we are again. It's the Physics 2A video lecture. The Physics 2A video lecture 11. And this time it will probably not be not quite as long, but we have an important topic because this week's lab is going to be in the same chapter. And we're talking about calorimetry. So this week's lab, I'll put this up as a note, calorimetry. Right, I should call it the virtual lab. It's the online lab, and we're in chapter 11. But we're just gonna always, as always, review some thermal physics and then continue on. So, we started with the sensation of hot and cold. So simply hot, cold. Then we talked about thermal expansion as one important phenomenon. Thermal expansion. Then from there we were able to have thermometers and temperature scales. Temperature scales, which allows us to measure these things and be a little more precise, reproducible. And in particular, we then had the gas thermometer as a very interesting example. Because there the gas is expanding. And if we take, in addition to the phenomenology of the gas thermometer, the idea of atomism, so molecular motion, atomic motion, as something that's there, although you can't see it, then we arrive at the ideal gas law. And there's the phenomenological version of it, and then there's its derivation via the kinetic theory. So if we have the ideal gas law, and then we have the kinetic theory, and then we're associating temperatures higher and lower with kinetic energies of these molecules. So I'll put here atomism once again. And that's where we had arrived. So we do know that the whole hot, cold, and thermal physics idea is associated with the energy concept, kinetic energy, for example. So the energy in general is going to be expressed in ways that involve the temperature. And that's what we're going to continue with. So as our next topic, it's just going to be thermal energy, and I'm going to go ahead and write here the calorie. The calorie. Everybody's interested in calories, so here we go. And I have a demonstration that goes with this. I'm going to describe it for you guys. You guys can do it at home. Okay, I'll describe it well enough. So the calorie, what has calories? A stick of butter has calories. Okay, so you want to get a stick of butter, and a stick of butter, you know, has this shape. Here's a stick of butter. And if you read on the label, it'll tell you how many calories it has per ounce or per whatever units in there. So you're going to have the calorie, and what we want to do with this butter is make a candle. So you got the butter and you have the butter candle. Okay. And to make the butter candle, you take some cotton string and just press it into the butter. Okay, the butter can be not too soft, not too hard. Press it into the butter, so you need cotton string. If you have some nylon string, it's not going to work. It's just going to burn you. So you need some real cotton string. I don't know if pure cotton yarn would work that well, but cotton string of some type. You press it into this butter, and what happens is you just pressed it in and buried it in there, snipped the ends off, and you have an interesting object, then what you do is you put it upright like this. There's the wick coming out, and if you light that wick, you're going to get a nice little flame. It's going to crackle a bit. Crackling is due to some slight water content of the butter. Okay. So the butter candle, that's a project I recommend everybody give it a try. It'll work with margarine too, but if you have butter in the house, let's make the butter candle. Okay, so what does the butter candle have to do with the calorie? We know that the butter is said to have calories. So, butter candle and calories. We're still talking about the calorie, so next, this would be the demonstration, and you guys can do it at home. You've got this nice butter candle burning, and on a stand, you have a beaker of water above it. There's the beaker, it's got some water inside. Butter candle, beaker of water, thermometer says degrees Celsius. And as the candle were to heat the water, you don't actually have to do this, but the idea is there, right? Candle, flame, beaker of water, thermometer. As the candle heats the water, the temperature of the water increases. And the definition of the calorie is enough heat or thermal energy to raise the temperature of water by a certain amount. So let's go ahead and write down the definition of the calorie. 1 calorie equals heat that'll raise the temperature of 1 kilogram of water by 1 degree Celsius. That should be pretty easy to memorize even, right? Kilogram of water, 1 degree Celsius. That was a calorie of heat, okay, a calorie of heat. So there's our definition of the calorie, and I'll say a couple things. Also, if you write the calorie lowercase calorie, then it's 1 gram of water by 1 degree Celsius, okay? Gram. So this lowercase calorie is 1/1000th of the uppercase. That's what the uppercase letter is worth compared to the lowercase. So because of that, we can say 1,000 calories equals 1 uppercase C calorie. And this would also be referred to as a kilocalorie, equals 1 kilocalorie. But the uppercase one is the actual food calorie, so may as well memorize that definition with the food calorie. This was butter. It has a certain amount of calories. As it burns, it raises the temperature of water by a certain amount. Good, so it's a good project and it's an important concept, the calorie. You see it comes from heat, thermal physics. Well, leave it at that. It comes from heat and thermal physics. I do want to mention one thing. Heat of combustion you could find a whole table of these, but often on our food labels they even say something like this: fat has 9 calories per gram. What else do they have? Carbohydrate, they will say 4, and protein, that would be also 4, and alcohol has about 7 calories per gram. Okay. So those are heats of combustion. And what's important is that anything that can burn is somewhere in this range. So gasoline, olive oil, butter, it's going to be up here in the 9s because fuel and fat is fuel. So you don't have to worry that there would be a whole huge range of them. This is basically what fuel has in it. So and so many calories per gram roughly these amounts. You could be talking about wood, we can talk about other things as well. How about lettuce? How many calories in lettuce? Well, lettuce is almost all water. If you were to dry it out enough, let it dry till it's just flaky and a little bit of fiber, and then you were to burn that, you would find out how much caloric value it has. So that's how it's done. All these calorie values of the whole list of foods in the world come from reducing it, getting the water out of it, and then just burning it and doing a careful measurement. Okay, so that's worth talking about, and there we have it. And if you do the demo, you really get your money's worth. The next thing we're going to do is relate this to the other energy concepts. I think I'll leave this up on the board and erase these definitions. Okay, so we have the calorie, but what about all the energy in terms of, say, the kinetic theory? The next idea I'll bring in then is called the mechanical equivalent of heat. Mechanical equivalent of heat. So when you're thinking heat, you're thinking the calorie now, okay, a certain amount of heat. And in the problem set, there's a thing called the Joule churn. I don't think they put it in the body of the text in the book, but in the problem set, there's a picture of a churn. You can churn butter, but here Mr. Joule made a device here where you could churn. It's kind of hard to draw. Imagine some paddle wheels in here. Okay, pretty good. You'd have water in there, you'd grab the handle and you just churn it, and there's resistance, right? There's a lot of resistance to churning it, and that means you're doing work. And if you're doing work, that means you're putting energy into the water there, and that is actually raising the temperature of water. So the Joule churn, churning this thing, doing work on it, let's imagine there's a thermometer in here, and as we churn the water, the temperature increases. So mechanical work turns into calories. And with a very careful experimental evaluation of that, here's what we find. We find that 1 calorie with the uppercase C is equal to 4,186 joules of work. That's how much work is done to raise the temperature of a kilogram of water by 1 degree Celsius. 4,186 joules. Now, how much work is this? I always like to use the old stair climb, which we probably talked about earlier in some connection this semester. So we've got the stair climb to the stairs, and let's say it's 5 meters, and it's 80 kilograms. So the work is mg, which is my weight, times h, which is the height, right? Potential energy or work. And if I have 80 kilograms, 10 meters per second squared, and 5 meters, then how many joules is that? Shows some good numbers here, right? 4,000. So in terms of just pure work, that stair climb is 4,000 joules. A calorie is 4,186 joules, about the same. Probably when we climb the stairs, we're using more than just 1 calorie because we're not 100% efficient machine. Okay. So there's a little bit of information about that in the text as well, but this is always a nice numerical example. Okay, you climb a lot of stairs to equal, say, a Big Mac or a Snickers bar or something. Or a stick of butter. A stick of butter has 800 calories, okay, that's a whole lot of stairs. Be that as it may, so we've got this mechanical equivalent of heat, and now we can, realize that we've just transformed work into thermal energy. Again, early in the semester we were doing mechanics and we said there were collisions and the energy was lost. Actually, the energy is converted into heat. I have a nice example, two nice examples for this idea with the collision and the transformation into heat. I was doing a homework problem. I'm not sure if I can assign it, but you guys can look it up. So let's imagine a collision and the production of heat. I had mentioned pounding on a nail. If you pound on a nail with a hammer, you grab the head of the nail, you'll see it actually gets warm. This is a practical matter. So, the two examples I'm going to give for the mechanical equivalent of heat, one is a bullet. So here's a bullet, and it's going to smash into something. You either hit a tree, in the book it hits a tree, or it can smash into plate metal or something, okay? So the bullet's going to come to a stop. It has a half mv squared of kinetic energy, and when it comes to a stop, it's just going to be smushed and it will be warmer. So let's suppose all of that energy was converted into heat. Actually, I have to put a question mark here first. Suppose that all of that energy were converted into heat. So what form would it take? Okay. What form would it take? Another example, so this was the bullet. Okay, I already wrote bullet. The second example is the waterfall. So we've got water flowing over the waterfall, and then it comes down here, it flows away. Is the water warmer at the bottom here? And after all, it's fallen and collided with the ground, with the rocks and stuff. So the waterfall is also a question of that. But interestingly, we can say the energy at the top of the waterfall was mgh compared to the energy at the bottom. It fell, it picked up speed, then it collided. So the concept that we need before we can answer these kind of questions is specific heat capacity. Because not every substance reacts the same. So what I'm going to do is draw a cartoon I like, and I just have an object here, and I'm representing heat flowing into this object with the letter Q. Okay, so the thermal energy flows into the object, the letter Q, and it's an object of mass M. And what we have then is Q, right? Thermal energy flows in and raises the temperature. So what we have here is Q equals MC change in temperature. So this is a certain amount of thermal energy. We know we can measure it in joules, okay, because calories are measured in joules. So we're going to say it's in joules. There's the mass, there's the change in temperature, and this is what's called the specific heat capacity. And I'll just write specific heat. And always the units. What are the units of this thing? At this point, you guys should just be reading them off, okay? So we're gonna isolate this thing. So the Q has the units of joules. We divide through by the mass. That's kilograms, and we divide through by the change in temperature. That's degrees Celsius. So that's the specific heat capacity units. Okay, I'll leave this up here so I'm going to raise this board now. So then you'll see that there's a table of specific heat capacities for all manner of substances, and they differ by quite a bit. There's one that we know by definition now, because if we have Q here in joules, 1 kilogram, 1 degree Celsius for water, what is that? Calorie, 4186 joules. So the specific heat capacity of water has already been fixed by definition here. So we have C sub water equals equals 4,186 joules per kilogram degrees Celsius. Kind of surprising, but metals have a much lower specific heat capacity. Water, in fact, is the champion of them all. It has the most, has the highest. So the other ones I don't memorize. You'll find them in your book. The lab that we usually do, we have copper, and I think it's 800 joules per kilogram degrees Celsius. Look it up, lead, steel, etc., different specific heats. So I'll just write C table in the book. This is chapter 11 that we're talking about. So there's specific heat capacity. All these different substances, water we know. Now, we can answer those questions up there. So for the bullet, if it's moving here, has kinetic energy half mv squared, and it smashes into the wall here, then that turns into this other formula. Okay, so the energy, let me just write it under here a little bit lower. So we have kinetic energy, it's going to smash into the wall and be heated up. And so that's going to be mc delta T. Okay. So this is the transformation of kinetic energy and just the heat of that metal, increase in temperature. And in fact, if it's moving fast enough, the metal could not only just heat up, it could actually melt. Could go past the melting point. If it was going fast enough, it could even vaporize, okay, which we're getting to soon. So that's the bullet idea, and you see the masses actually cancel out, so a problem like this would be easy to solve. What about the waterfall? So the water falls off the cliff, and it starts up with this much potential energy at the top, and at the bottom, it lands on the rocks, and then we could say mc delta T. So depending on the height of the cliff, we'd get an increase in temperature in the water. You may want to run some numerical examples by. It could be a very, very high cliff and not get much of a change in temperature at all, based on the value of the specific heat of water here. Okay, good. So that's the specific heat, and we now have some examples, even starting before the actual definition, because we have the calorie, the butter candle, we have the mechanical equivalent of heat, and we have the specific heat capacity. So all of those concepts you want to write down in order and understand. Now we can get to calorimetry, which is the topic of our lab this week. So let me see how much time we've been spending here. Okay, calorimetry is the next topic. I'll write down these concepts in a list, and then we'll move on to this next one here. Okay, so calorimetry. The idea is that we bring two objects into contact with another and wait until the temperature equalizes. So that's the first thing we have to know. So bring objects into contact. Objects into contact. Let temperatures equalize. And this could also include just taking some cold water and some hot water, pouring them both in a beaker. And then what's the final temperature, right? You stir it up, eventually it's just one temperature, and what is that? So there's our task, and the way it's often done is you have some water here, and you have an object, and you're just going to drop it in the water and measure the change in temperature and measure the final temperature. Okay. So this is object 1 and the water is object 2. The beaker itself will be in the problem. Say it's aluminum beaker, then the beaker itself is object 3. The idea is that the entire process be done in an isolated situation. The idea is that there's no heat escaping here. So any heat that escapes from this number 1 piece will be absorbed by the water and everything else. Okay, so the energy is constant. Total thermal energy is constant. And I like to use the letter Q. Well, let's save that for later. So that's a scenario. You're dropping something hot in here and cools off and the temperatures are involved. So here's what we have. Since the total energy is constant, then Q1, I'm just going to start with 2 objects. Q1 plus Q2 is equal to 0. Because if this one increases, this one has a decrease. So our next step would be to say we have M sub 1, C sub 1, delta T, and we have M sub 2, C sub 2, delta T sub 2 is equal to 0, right? This was MC, change in temperature of one object. I got my definition right up here. MC delta T of the 2 object. Now here's the crucial step. M1, C1, T minus T1. Let's just write this down and understand it. So M2, C2, T minus T2 is equal to 0. This one I'm going to put in a box and we're going to focus on it. Once you can do it for 2 objects, you can do it for 10, okay? It's no big deal. So what we're looking at is the following. The change in temperature is the change from the final temperature minus the initial temperature. On this one as well, it's the final temperature minus the initial temperature. So they started with their own temperature, T1, this one had T2, but they ended with the common temperature T. So for example, in this problem, it's one equation, one unknown. You can solve for one unknown. You can solve, for example, for the final temperature. You crank out a little bit of algebra, final temperature is so-and-so. And now if you have 1, 2, 3, 4, 5 objects, you do Q1 plus Q2 plus Q3 all the way to Q5, still equals 0, and it just gets more tedious. It's not difficult though. You write the whole thing out, and then you can solve for one unknown. So it can be a lot of arithmetic just for one unknown. But that's what you get out of this equation. And thermal energy being constant is just conservation of energy. We're saying it's shut in here, it's not being lost any which way. And if you do it this way, sometimes the book will say, Q1 equals Q2. If you do it my way, which is the better way, you don't have to worry about the signs. The sign takes care of itself. In one of these, the final temperature will be higher, and one of them it'll be lower. But you don't have to worry about that. You just, write down this definition here in this equation. Like I said, the signs take care of themselves. Okay, so let's do a couple of examples. And I think then we'll leave it at that. Okay, so the example I want, first of all, is just mixing water. So mixing water of 2 different temperatures, different amounts of water, different temperatures. So that's a nice example. This is the kind I can put on an exam without fail. Okay. Yeah. Yeah, I'm going to mention something about these specific heats. You know, they're kind of wild numbers, 4186, 800, 350, and so forth. On the exam, I can just make up some clean round numbers, and we can do the same kind of problems that way. So the idea always is no calculator, right? So the example is, let's mix 1 liter of water at, say, 90 degrees Celsius with 1/2 liter of water at, say, 50 degrees Celsius. Okay, I have no idea. What's the answer? What's the final temperature? T final equals question mark is what I'm going to write. T final equals what? Okay, so here's what we're going to do. We have MC T minus T1. Let's just write this down again. Plus M2C2 T minus T2 equals 0. I just copied that down again here. So a liter of water is a kilogram. So we have 1 kilogram. I won't even put the units here. We have 4186. Oh, actually, let's not even do that. I don't want to write too many numbers here, do we? So this is a simple problem because both of these things have the same specific heat. Okay. So the next thing to do would be to copy that down, but we can actually go to the numbers. So we're going to cancel C1 and C2. We're going to have 1, and then T minus T1, it will be T minus 90 plus 1/2, this was common, T minus 50 equals 0. Okay. And now you want to solve for the final temperature. So you'd have T minus 90 plus T over 2 minus 50 equals 0. And I see we have 3/2 times T is equal to 140. And then T would be 2/3 of 140. Okay. So that's one example, and you always start here and then simplifying with your algebra. Now, I could just write one out for more of these. Let's see here. Let me check this thing before we move on. Yeah, I see a problem right here. I see a problem right here, and we are doing one take, so let's make sure we get this right before we leave the topic. Okay. So the specific heats were the same. We have T minus 90, T minus 50. So T minus. there's my mistake. All right, got to catch your mistakes in real time. Okay. Okay, no, there's no edit on this tape, but here we go. So what we have is t plus 1/2 t is equal to 90 plus 25, not 50, because I had the t over 2 there, is equal to 115, and therefore t is going to be 2/3 of 115. Okay, it'll be degrees Celsius. Okay, yeah, that can happen sometimes. I realized that the final temperature was going to be higher than 90. That could not be the case. Okay, good. So we have that. Now let's just write down a slightly more complicated one. And then we'll call it good. Okay, so this one, we have some copper that we're dropping into some water. So we have copper. We're going to drop it into this beaker of water, but the beaker is made of aluminum. This is the way our lab goes here at Fresno State. That we would have done if we weren't doing this online business. So now we have copper, water, and aluminum. And so we'll have to say mass of copper, specific heat of copper, T minus T of copper, plus mass of water, specific heat of water, T minus T of the water, plus mass of the aluminum, specific heat of the aluminum, T minus T of the aluminum, equals 0. Should have left a little more room here. Equals 0. Okay. So we've got an equation here, whole thing equals 0. And again, we can only solve for one unknown, but the interesting thing here is if you know the specific heats of everything but one of these, you can use it to measure the specific heat of your new substance. So suppose you knew water we knew, right? Suppose you already knew aluminum, then you could throw copper into the mix and now learn the specific heat of copper. And so one by one, you could get the specific heat capacities of all substances. If you had an unknown one, it could be a mix of things, you could get its specific heat capacity as well. So it's always one equation, one unknown, but you can systematically work your way through different materials and discover their specific heat capacity. Okay, good. I'm going to leave it at that and put a homework assignment up that covers both of these topics that we talked about today. And then on the next lecture, we'll continue on and try to wrap up chapter 11. What we did today is really directly in the lab, so I wanted to make sure you see that. Okay, so this is to be added to the ones we had in lecture number 10, and we're looking at chapter 11. There are a couple of problems just with the mechanical equivalent of heat, basically, and then there are some with calorimetry. So 612, 1929, and 31. Good, so let's leave it there and take good notes as always. Leave a lot of space. You can fill in some stuff you didn't get the first time, and we'll see you next time.